Okay, people, we got 29. That's 3/5. Okay, we're almost ready to go. I don't have a whole lot to talk about today, so I'm going to wait a little bit for people to show up if they're going to, and then we'll get going. Hey there. I got two people on one screen. That's cool. Okay, I'm getting anxious with everybody looking at me. I guess you can tell I'm in the bedroom on the bed. What are you gonna do? Got to go somewhere. Okay, so I'm going to open up discussion today. Oop, chat's open. Hello, Professor. Hello, Saksham. You're a good man, Saksham. Where is my PowerPoint? There it is. That's not what I want. Come on. There it is. Okay. Opening my chat window. Trying to open my chat window. Come on, man. Hang on. My chat window won't open. Okay, Lexi Michelle. Lexi Michelle, you're one of the few people whose faces I can see here, okay? So keep your chat open. Keep your chat window open. If anybody chats, wave to me and I'll stop, okay? Because I can't see my chat window here. Okay. All right. Here's the deal, people. This is one of the kind of important grand concepts in this class. How do drugs work? How is a drug going to produce an effect? So what drugs do is bind to a protein and either activate it or block it. Okay, that's all they do. So we went through all the mechanisms of how information's passed through synapses, and now basically you can design a drug to either activate or block any protein in this system, and that will change the transmission there. So if you look at this, so what we've got here, it's basically two figures that I jammed together. We've got our synapses here. We've got the enzyme making neurotransmitter, the enzyme pumping neurotransmitter in. We've got the calcium channel. Don't necessarily, I shouldn't have that red X there. And we've got neurotransmitter out here, the pump taking it back in. We've got our postsynaptic receptors, which are inotropic. They look like inotropic receptors here. Okay, so question, how do I do this? Well, let me just ask, can anyone come up with the drug mechanism by looking at this? In other words, just tell me what protein you're going to interact with and what you would do with it and how that would affect synaptic transmission. I'm waiting. I'm still waiting. All right, I'm going to start picking on people because I'm guessing no one's going to answer unless I do. Julia Waterus, you haven't said a damn thing all semester. Let's see your face. Unless you don't want to show your face, but it'd be nice to see your face. Julia Waterus, are you currently here or have you gone away? There she is. Okay. So if you were going to design a drug to do something to the synapse, what do you think you might do? Okay, let's pretend. Where are you? Are you in your dorm room? I can't hear you. You got to unmute.
I did.
You're what? Where are you? Probably chatting, and I can't see the stupid chat window.
Your microphone isn't working.
Oh, your microphone's not working. Oh, okay. All right. Well, the hell with you. All right. Let's go to Abusador, to Johnny.
Yeah.
Can we see your face?
Yeah, sure. I don't have a shirt on, so I don't know.
All right. Don't bother then. Don't bother then.
Okay.
So if you wanted to design a drug, what would be your target here in this synapse? What might you do? Just choose one.
I would target the membrane maybe with the receptors.
Okay. What? Be specific. The membrane with the receptors. So you want to target the membrane or the receptors?
The receptors specifically.
Okay. And what would your drug do? Activate or block?
Block, right?
Okay, that's one mechanism. Okay, and that's how easy this question is really. Pick out a protein in this thing and activate it or block it. So one type of drug would be and that would be an antagonist. Okay, it would be a drug that binds to that postsynaptic receptor and blocks it. What's another drug? Tanner Tobias. You're muted. Weren't you Elena earlier? You're still muted. Can't hear you.
Oh, well, my bad. Yeah,
Okay.
I had somebody else was logged into my computer, so I had to change my name back.
Okay.
Didn't realize I was, but yeah, it would bind to the receptor and then activate it. It would just
Okay. All right. So
Okay.
that's the obvious next drug. An agonist will bind to the postsynaptic receptor and activate it. Okay, going down the list, Morgan Bailey, what would you do? Looks like she left. Boy, that's cowardly. That's cowardly. I call on her and she takes off. Okay, next on the list is Stephen McCain. There he is. Are you unmuted? You're not unmuted yet.
I'm not unmuted.
I like the flat top look.
Thanks, Marjorie Gerald from Hey Arnold.
Cool. I wish I had hair. All right. What do you think? Just pick another protein, activate it or block it.
A protein.
Yeah, something in this mechanism.
The autoreceptors. Let's
Oh.
let's activate.
Awesome. That's a good choice. The autoreceptor. Now you're gonna activate it or block it.
Let's activate them.
You're gonna activate it. So if you activate it, what happens to synaptic transmission here? Does it increase or decrease?
Increases.
Does it? Decreases, right. So if you're activating the autoreceptor, it's going to block that calcium channel and you get less neural transmission.
Okay.
Okay, well done, Dr. Stefan. Sydney Barriere, can you tell me how to pronounce your name? Because every time I look at it, I think Derriere, and that's just not right. Is
It's
that the way
barrier.
it is? Barriere.
Yeah.
Barrier, like a fence barrier?
Yeah. Yeah.
Okay, good. All right. So I will not make that mistake again. So tell me, what's another thing you can do here? Pick another protein, same protein, do some to it.
Activate the proteins on the postsynaptic membrane.
Yeah, we did that one already. That's the agonist that binds the receptor in the postsynaptic membrane. How about that autoreceptor? Let's go back to that. Stefan put a drug in there that would activate it and that blocked neurotransmission. What else could you do to that autoreceptor?
You can inactivate it and then increase the synapse.
Exactly. And there are drugs that can do that. Yep. Okay, well done, my friend. What else do we got? Sade James. Is it Sade? Do you
Yeah,
pronounce it? It is pronounced that way?
yeah, like the singer.
Are you a cool operator? Oh, that's bad.
I'm better than that.
That was so bad. I can't believe I even
Yeah,
said that.
it's
Oh,
alright.
I'm
It's
sorry.
alright.
I love that album though. All right, anyway. Pick another protein, activate or inhibit.
The uptake pump.
Yes, excellent. There are a lot of drugs that do that. So you're going to activate it or inhibit it.
I would inhibit it.
Okay. And what does that do to transmission?
Um,
Do you get more or less stimulation at the postsynaptic side?
less, more.
More,
When you
correct.
do that face, you like.
Yeah. So if you're blocking that pump, the neurotransmitter is going to stay in the synapse longer and you get more synaptic transmission there.
Okay.
Cocaine does that. Okay. What else do we got? DeJovany Jupiter. Another one of my favorite names, frankly. There he is. Like the hair too. Yeah, I think there's something wrong with your mic. I can't really hear you. Any luck? You know, I think we might just move on. Sorry about that.
Yeah.
It's okay. Okay. All right, Matt Cole, what do you got for me?
Activating the ionotropic receptors.
Oh, okay, yeah, that's good, but that's one we did already. That was the
okay.
first one.
Glutamate.
Glutamate. What are you doing with glutamate?
Inhibiting.
See, kind of what we're doing here is this is a general general synapse, so we're not looking at what neurotransmitter we're looking at. We're just going to look at this synapse, grab a protein there, and activate it or inhibit it, and how will that affect neurotransmission?
Okay.
Do we move on?
Yeah.
Okay. Robert Johnson, I've been wanting to talk to you forever. Come on up, Robert. Have you been down to the crossroads, Robert?
I can't say I have. I understand the reference, but no.
Okay, good. Have you sold your soul to the devil?
Not yet. I probably should, because I don't really have anything for you.
Let's face it, your soul ain't worth a whole lot anyway, so see what you can get. Okay, you don't have anything? Just pick out a protein there we haven't already picked out.
We did the autoreceptor and the uptake pump.
Right. What else we got there? I'm looking at 3 right now.
Yeah.
If I was standing behind you with a gun at your head, what would you say? You have to give an answer. Doesn't have to be right, but you have to give an answer.
It would probably just be a prayer at that point.
And we're back to your soul. Okay.
Yeah.
All right, let's move on. How about Carrie Murphy? There she is. Ms. Murphy. Oh,
honestly, which ones haven't we done?
Okay, so we've done the postsynaptic membrane. That's all set. We've done the autoreceptor and we've done the uptake pump.
I don't even know what's left.
Okay, just like anything there except a neurotransmitter is a protein. So pick one out and what does it do?
What's the thing you're pointing at?
That's what I'm asking.
I haven't. Mitochondrion? Someone wrote in the chat.
Oh, mitochondrion. That's another potential. That's another potential target. But what I was trying to get Miss Murphy on was this purple thing here. What does this do? Here it is. Here's its action. So this is a different pump. This is the pump that puts neurotransmitter into these vesicles.
Yeah.
If we activated and inhibited that, then the vessel would empty and you'd block neurotransmission. Okay, if we activated it, and some drugs will reverse that and spill all that neurotransmitter out. So that's another option. Okay, I only see 2 more things up here. Willie Corley, you're one of my smarter students. You're all one of my smarter students, frankly. Willie. Willie, are you awake? There he is. There he is. All right, I see 2 more targets up there. Yeah,
Is that better?
There, now I hear you.
Okay. So we did the postsynaptic membrane, we did the autoreceptor. Did we do pump, activate and inhibit already?
Yeah. How about this guy here? What's that doing?
Is that the enzyme that like, I don't know how to say it, it like puts the neurotransmitter together?
Right, exactly. So the synthesizing enzymes, you could block those with a drug that would block it. What would that do to synaptic transmission, up or down?
Decrease, because then you wouldn't have a neurotransmitter to go into the postsynaptic membrane.
Right, exactly. You could also put in extra precursors for the neurotransmitter and make the enzyme work more. Then you got more neurotransmitter in there. So that would make it work even better. All right, so the only thing left is a calcium channel, which is a really bad target anyway, because that's in all neurons. So if you wanted to block, say, norepinephrine transmission, and you block calcium channels, everything would stop and you would die. And that's what we, as pharmacologists, that's what we want to avoid, having patients die. Okay, so I've summed this up on the next page. What can a drug do in a synapse to affect synaptic transmission? The last thing I said is the first thing here, serve as a precursor for neurotransmitter synthesis. So there's a drug, L-DOPA, which people with Parkinson's take because it gets into your brain and then it gets converted into dopamine, increases dopamine release and blocks some of their symptoms. You could inhibit neurotransmitter synthesis. Trying to remember one for norepinephrine. It was a plant product. Can't remember the name of it, but it blocks synthesis and that decreases norepinephrine in the synapses. Prevents storage of neurotransmitter in vesicles. So not sure what that means. I guess if you reverse that pump, the neurotransmitter would come out. I don't know what that means. I don't know where I got this now. Okay, stimulate the release of neurotransmitter from vesicles, and we have drugs that do that. Amphetamines will do that. Just dump all the neurotransmitter out of the vesicles into the synapse, and then they reverse the uptake pump and dump it all out of the nerve terminal. Inhibit fusion of vesicles at the nerve terminal. Botox does this. It blocks vesicle fusion, and so that blocks neurotransmissions. That's why, you know, if you're one of these people who did this all day long, you end up with lines in your head. So they inject Botox in your skin, and then you look like this all day. But anyway, you block neurotransmission here, and then you're not doing this all the time. You don't get wrinkles in your face. Activate or block postsynaptic receptors. That was the first thing we talked about. Activate or block the presynaptic autoreceptors. We talked about that. Inhibition of neurotransmitter degradation. We didn't talk about that. So not a lot of neurotransmitters are broken down. Acetylcholine is. So if we block acetylcholinesterase, that will increase acetylcholine in the synapse, and that will change transmission. Block the reuptake of neurotransmitter. That's a pretty popular one. Reverse the reuptake pump, dumping out whatever neurotransmitter happens to be in the synapse. So we've come up with at least 10 here, and we may have even talked about a few more that aren't written here. But the basic idea I'm trying to get across with this exercise is, if you know all the proteins involved in the synapse, a drug could be designed to activate or inhibit any one of those proteins, and then that's going to change your neurotransmission. And that's the way, you know, drugs are made, basically. All right. And besides, this is the kind of question I really like to ask on exams. I may say, a drug is found that causes X effect. How do you think it produces that effect? So if it's like a drug is found that decreases norepinephrine's effect in the brain, how does it work? Well, it could inhibit its synthesis. It could block its postsynaptic receptor. It could empty the nerve terminal so there's nothing in it. There, like every little spot in that pathway could be blocked by this drug in some way. And then your job as a pharmacologist would be to figure out how exactly it's producing this effect. Okay, everybody happy? Or is it just me? Okay, we move on. All right, so receptor regulation. Sade, did you have a question? You just
No,
lit
I
up.
was just gonna say just you.
Well, I'm getting paid, so I should be enjoying this. So anyway, receptor regulation. So this is a really important concept. The basic idea is, and you know this from your own life, the more you get exposed to something, the less interesting it is, the less good it is. So for example, when you first start, when you say you're really hungry and you get a big cheeseburger in front of you or a veggie burger if you don't eat meat, and that first bite, oh, it tastes so good and you feel excited that you got this burger. By the time you get most of the way through the burger, it's okay. It's not great, but it's a burger. It's good, you know. But every experience you have, every drug you take will have a strong effect at first, and that effect will decrease over time as you keep being stimulated by it. And the reason for that is because of receptor downregulation. So when a receptor gets activated by the neurotransmitter, it then turns on some second messenger system. In this case, we're talking about cyclic AMP. So cyclic AMP then activates protein kinases. We talked about that in the last class. And this protein kinases go off and produce whatever effect they're going to produce in the cell. Well, one of the feedback mechanisms here is once you get that kinase activated, it comes back and phosphorylates the receptor. Phosphorylation of that receptor then leads it to move across the membrane and end up in these pits. And the pits then endocytose, and it takes those receptors out of the membrane. So if you overstimulate these receptors, you get this feedback mechanism that pulls the receptors down out of the membrane. And if you continually overstimulate, those receptors will go to the lysosomes and get degraded. If you take the stimulus away, they'll go from that internal pool back up into the membrane, and then you get back to normal. And on the other side, if you understimulate, the cell will put more receptors out there in order to get some stimulation out of the neurotransmitter. So it goes in both directions. And I've got this animation I want to show you, which is, I made it for cell biology. So there's a lot more details here than you need to know. But it's one of these flash animations that I made years ago, and in December they're all going away, so I want to use it as much as possible while I can. But come December, you won't be able to watch this on Google Chrome anymore. But anyway, here's our receptor. In this case, I'm calling it beta 2, doesn't matter why. Here's our neurotransmitter. Here is the G protein. Now, when I said G protein in the last class, I just made it one circle, one protein. It's actually 3 proteins. Not that important for at your level right now. Just think this is the G protein. And then here's some other proteins that are not that important to you either. Arrestin, which is going to be part of the mechanism. And here's our kinase that's going to be activated. All right, so here's how this works. The neurotransmitter binds to the receptor, changes its conformation, and in that new conformation, it then activates the G protein. And again, there's detail here you don't need to know at your level. Okay, so the G protein goes off and produces an effect. Now the feedback is this. This kinase is going to come up and phosphorylate the receptor. Sometimes they give off a pop. And now this is just kind of an intermediary protein that ends up in the mechanism. You don't need to worry about that. Okay, but the point is the receptor has been phosphorylated. Now it goes into this pit, and endocytosis. Okay, so now this receptor can't respond to the drug or the neurotransmitter anymore because it's inside the cell. All right, so that's kind of like the close-up view of what's going on with one receptor. But you want to think about it in terms of what's going on in the whole cell or in the whole postsynaptic side of the synapse when this is going on. So the total number of receptors in the cell membrane then is going to be under control by 4 different processes. Oops, let's do this. You've got you know what? I'm not going to go through this because this is more detailed than you need to know, but I want you to watch the animation of it anyway. So here we've got new receptors being put in the membrane. We've got new receptors being made over here, and they go into this membrane pool here. And we've got receptors being degraded and receptors internalized. So basically you've got this internal pool here that's in equilibrium with the surface and with the lysosome and with the other thing. So when you've got a constant amount of stimulation, you'll have a constant amount of receptors in the membrane. These little yellow flashes are stimulation. So now let's throw a whole bunch more neurotransmitter in there. These little bouncy things are neurotransmitter. Let's watch how much more we got now. Boom. Booyah. Now we got a lot of stimulation. And so because the cell is being overstimulated, it's going to start degrading receptors and internalizing them. We're not putting any more out. We're not making any more. We're degrading and internalizing. And so the result is over time, you've got fewer receptors here. And now you're getting the same number of flashes you got before because you still have a lot of drug out there, but you've got fewer receptors. So you're no longer really stimulating that cell. If you do the opposite, here, these little yellow things are blocking the receptor. So these are antagonists blocking the receptor. We've got no stimulation of this cell anymore. So now the equilibrium is going to shift towards putting more receptors in the membrane and making more receptors. Or making this cell more sensitive, super sensitive to the neurotransmitter. And once you get enough receptors out there, you're out competing the antagonist, and now you are getting stimulation again. Now we're back to the amount of stimulation we had at the beginning with more receptors because we're blocking a lot of the receptors with the antagonist. Someone just gave up on me and went home. That's okay. That doesn't bother me. Oops. Wouldn't the body want more receptors to absorb the stimulus as the level at the level as stimulus increases so it may metabolize it? Yeah, there's a lot of confusion there in that. Okay, so wouldn't the body want, so don't worry about the body, leave the body out. We're talking about the cell level. Want more receptors to absorb the stimulus. Well, see, if you've got more receptors, then you get more stimulus. Okay, so the stimulus is all about neurotransmitter hitting receptors. So if you put more receptors out there, like you're getting overstimulated, you put more receptors out there, now you got more stimulation. So it's the opposite thing you want to do. If you've got too much stimulus, pull the receptors away, bring that stimulus level back down. And metabolism happens somewhere else. So let's not confuse those two things. This just happens at the micro level here with a neurotransmitter and receptor and how the cell responds to the neurotransmitter or a drug that activates that receptor. Okay, does that make sense?
Yes.
Okay, good. What else do I got for you guys today? Oh boy. Okay, so one thing I like to draw on the board, I like to draw something on the board that helps this to make sense. And I don't have that figure here, but I'm going to draw it for you so you can see what I'm thinking about in terms of these drugs. I always draw this on the board and people It kind of gets the point across really well, so I want to do it for you here. Just give me a minute to get a file open so I can start drawing. Come on, come on. Create a new one. Daddy don't have time for this. Okay, let me share this with you. Okay, so pretend I'm drawing on the board. So here's a little graph. And on the bottom, we're going to put time. And I'm just going to say time. I'm not going to give it units. Time is on my side. Sorry. Rolling Stones joke. And then over here, I'm going to put mood. Okay, so in terms of mood, what is your mood like day to day, right? Some days you're high, some days you're low. So your mood can change a lot. So let's put a line down the middle. Make that better. Here's the middle. Let's give this a little weight. And make it a dashed line. Okay, so this middle area, we're going to call, let me zoom in on this so you can see it better. So this middle thing here is normal. This is your normal mood on a normal day. Nothing special. You don't have Dr. Slish today, so nothing's too exciting. Just relaxed, boring day. All right, so that's normal. That's your mood on a normal day, right? Okay, so on a bad day, you're going to feel blah. Okay, a bad day is blah. You can see how scientific this is. And then a really good day, best day of your life, you feel great, okay? So you've got euphoria and you've got blah, you feel really crappy. So you're somewhere around there. And, you know, day to day, you kind of do this a little bit. A good day, bad day, you know, good meal makes you feel good. Got to do laundry, makes you feel bad. Okay, so let's say you're on a normal day, right? Oops, let's not do that. Oops. All right, so let's say I'm going to start you here. Okay. So here's your mood today, right? Right, a little better. It's a pretty good day. It's Friday night, okay? Everything's kind of heading somewhere, so you're feeling pretty good. You get to where you're going, and someone there has some cocaine. What happens when you take cocaine? Woo! Now you're way up in the Yahoo area. Okay, you take that drug, Let me specify that. By the way, I'm going to put this into your PowerPoint when I'm done because it's actually a pretty good thing to have there. Oops, not that. Okay. Okay, Mr. Illegal Drug User. Took your Coke here. And it makes you feel good. That's why you did it, okay? So, thing about cocaine, I don't know if any of you have done it, I hope not. Hope you don't do it anyway, because the problem with cocaine is it doesn't last very long. If you're doing crack cocaine, it'll last like 3 or 4 minutes. If you're doing powder cocaine and snorting it, it'll probably last a half an hour to 45 minutes, but it doesn't really last all that long. So what happens when the drug goes away? When the drug goes away, you come down to here. Okay, why is that? The drug goes away, but while the drug was high, your body, your cells started pulling your dopamine receptors out of the membrane, so that because it's getting overstimulated, so it pulls them away. So now you're not just breaking even, you're a little bit lower than even. So what do you do? What do you do when it's Friday night and you've run and you're not feeling good?
Take more.
You take more. Rehab is for quitters. You take more. And you get back up. Now notice, we're not going up as far as we were last time, right? Why is that? Because we don't have as many receptors, okay? You take the same dose of drug, you've got the same amount of dopamine being released, but you don't have the receptors there to respond to it, so you can't get quite as high with that peak. And then another half an hour later, we're down here. Okay, because now we're continuing to overstimulate those receptors. And so now your cells keep bringing them away. You've got fewer and fewer receptors because it's trying to find this homeostasis level of the mood. And you keep perturbing it with that cocaine, taking you way too high. So now the body's trying to, curb your enthusiasm. Come on back down here with the rest of us. So what do?
Take more.
Take more. You're not a quitter. Okay. Now what? Ugh. Now it's not affecting you as much, right? Take a higher dose, it may produce more of an effect, but now you're worried about side effects. And then when that dose runs away, this, and then this, and then this is Saturday morning. Oh, never again. I'm not doing that anymore. That really sucks, right? Because you've totally overstimulated your cells. The receptors have come away, and now the normal amount of dopamine in your brain is not enough to get you back up to a normal mood. So now you're going to feel crappy for a while. And over the period of the day, or maybe by the next day, your receptors will come back to normal, and you'll feel normal again. But this is kind of what happens when you repeat dose with the drug. You're down regulating receptors, and then the drug has less of an effect. Okay, that makes. Let me see your faces real quick.
My camera's not working.
Okay, well, if you've got a camera, let's see you.
My wig is not on.
That's okay. I should get a wig. Okay, so does everybody understand the part we said by show of hands? Everybody understand the part first part about how drugs work? Because you will see that on an exam probably. Yes? Just find a protein there, inhibit it or activate it. Okay, how about down regulation? Everybody get that? Yes? No? How about show of hands? How many people thought that was okay? Okay, sounds like you're doing pretty well. So class is 40 minutes. Normally this would take me an hour and 15, but here we are. So I think we're done now for everything we want to do for the exam. So our exam is scheduled for next Thursday, which means we've got Tuesday free. I think what I'm going to do is come up with a practice. I'm sorry?
Thursday? I thought it was Wednesday.
What's today? Wednesday. Yeah, our exam's Wednesday. Sorry. I've got Tuesday, Thursday, and Monday, Wednesday classes, and I always confuse those. So anyway, our exam is next Wednesday. So Monday, why don't we all get together? I'll give you a sample exam, give you about a half an hour to quickly go through and write answers down, and then we'll talk about the answers, and I'll let you know what I expect on an exam and how to read these questions, because usually the questions are a little more complicated. They're not just, black and white. What is this? Oh yeah, I memorized that from the test. But you know this information from what we learned in class. How do you apply that to a new situation so that you can, solve a different problem? So that's kind of what the questions are like on the exam. And sometimes people aren't used to that kind of a question. I know Julia Waterhouse is used to it because she's had me before. You were in 2 of my classes last year, weren't you? Cell and developmental, or just developmental? Yes, you can't talk. We'll leave you alone. Okay. Any questions, comments? No? All right. Well, I'm going to let you go.
Yes, somebody wrote in the chat. Somebody wrote in the chat.
Thank you. Who was supposed to tell me about the chat? Somebody was falling down. Yeah, Lexi. Thank you, Lexi. Oh, Julia Waterhouse, just developmental. Okay. Any bonus questions during the exam? Not usually, no. We'll work out some bonus possibilities later. Stefan, I'll email you. Private question there, so I'll email you. And we'll talk about that later. Okay, any other questions? All right, well, I'm gonna let y'all go. Have a great weekend, and I'll see you on Monday. Make sure you study, okay? Don't show up not doing anything. Study this weekend. Later, guys.